I'm Christopher Tapia Carmen, and this is my Physics 2212 Lab 6 Faraday's Law. The content in this lab include purpose, procedures, physics, and error that may arise, and then finally questions. So the purpose. The purpose of this lab is to see how magnetic fields create a magnetic force, and then how those interact with the surroundings and the conductors. So conductors include a copper tube and aluminum tube that we use. So procedure. So what you need is a tube, aluminum or copper does the work, a magnet, a phone to record, a meter stick, and then a computer for the computational model. So what you do is you put the magnet through the tube and see how long it takes to fall. You want to compare it to like a realistic free fall, so just do a normal free fall as well to see how it differs. To actually see how it differs. So physics behind it, we know that there's a magnetic flux which is increasing as it goes down. Like each ring has an increasing flux, so that means that there has to be an opposing flux to oppose it, since that one's increasing. And so as a result, the copper acts like a solenoid of multiple rings, and those rings each exert a induced current going up, and thus magnetic force going up, and slow down the magnet as it drops. Alright, this is our video. As you can see, it takes more time than normal to for the magnet to fall down. We ran 3 trials, and then the average was 1.24 seconds. Compared to the free fall, which was around 0.43 seconds. The length of the meter stick was 91.5 centimeters with 2.54 centimeters of diameter. Code. So this is the computational model. So over here we have normal constants. This is just for a graph. Our length was, like I said, 0.195 centimeters or 0.195 meters. And then I just plugged in everything else here. This loop just creates like the vectors, and then like the images. This is just constants. This also creates like visual. Code continued. The definition dipole B just explains the magnetic field of the magnet as it acts as a dipole. Then the def calculate D flux. This is just to calculate our change in flux as the magnet travels. This whole function here is the most important one, which actually goes through each and every like instant and slash like number of loops, and then calculates basically the magnetic force that it exerts on the magnet as it's falling down, and then it gives us a value, and it just does that multiple times. Yeah. Alright, so these are our results. As you can see, velocity, and then almost at probably when it reaches like the magnet fully is inside the tube, it reaches like a constant velocity, and then it just, when it goes out, it just drops. And then you can see the time is 2.956 seconds. Alright, so any error, basically there was unaccounted resistance like air friction, and then air resistance and friction maybe. Timing from the phone, when we use our phone, obviously like there's it may not be as accurate, and then maybe not accurate measurements of the tube, because well, the meter stick is like obviously not, it's accurate but not to the like decimal. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? So basically we know EMF equals IR, and if we know that, that means that I equals EMF over R. So if R is basically 0, that means it's like going to infinity, meaning that the current is really strong upwards, basically saying that the magnet's gonna stop moving and then just like stay there, completely oppose gravity. And then what if holes or slots were cut into the tube? How would this affect the ring currents in our model? So basically, if there was like holes, then there wouldn't be rings and it wouldn't be a solenoid. Therefore, it would not. It would just basically be in free fall.